Hi class, in this video we're going to talk about the integral test, and then at the end of it we're going to talk about p-series. All right, so in general it's difficult to find the exact sum of series. You've seen it in your homework online and in some of the videos and examples we've done. But we were able to accomplish this for geometric series in the series when we looked at the summation of 1 over n times n plus 1, because in each of these cases we could find a simple formula for the nth partial sum s sub n. But usually it isn't easy to discover such a formula, as you've seen as you've tried to go through your own examples. All right, so let's begin by investigating the series whose terms are the reciprocals of the squares of the positive integers. Meaning we take this summation from n equal 1 to infinity of 1 divided by n squared, and you can see what each term starts to look like. So when n is equal to 1, it's 1 squared, 2 squared, then 3 squared, then 4 squared, 5 squared, da, 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 so on and so on. All right, so what we want to do is we want to investigate what this sum is. All right, so there's no simple formula for the sum s sub n, all right, of the first n terms, so you can't find the partial sums. But the computer generated table below of the approximate values given in the margin suggests that the partial sums are approaching a number near 1.64 as n goes to an infinity. So like this is what the n partial sums are. So like this s sub n here are the first 5 sums, then the first 10 sums, 50 and so on. And so what we see here is it looks like this series is convergent to something. All right, we can confirm this impression with the geometric argument. So figure 1 shows the curve y is equal to 1 over x squared and rectangles that lie below the curve. All right, so here's the curve y is equal to x squared, and this is a rectangle below it where the area is 1 over 1 squared. This rectangle's area is 1 over 2 squared, and you can see that these areas here represent the individual terms of this summation right here. All right, so the base of each rectangle is an interval of length 1. So the height is equal to the value of the function, all right, at the right endpoint of the interval, as you're seeing here. All right, so the sum of the series of the rectangles is the following, as we've seen. If we exclude the first rectangle, all right, so if we exclude this one right here, the total area of the remaining rectangles is smaller than the area under the curve y is equal to 1 over x squared for x is greater than or equal to 1, which is basically, remember area under the curve, which is basically the value of the integral from 1 to infinity, 1 divided by x squared dx. So the improper integral is convergent and has value 1. So the picture shows that all the partial sums are less than, so you take the first rectangle and add it to this integral that we used to find the area from here underneath the curve. Now note that that's not what the total sum is equal to. All we're saying is that the sum of this has to be less than 2. All right, thus the partial sums are bounded. All right, we also know that the partial sums are increasing because all the terms are positive, obviously. Therefore, the partial sums converge by the monotonic sequence theorem, and so the series is convergent. So the sum of the series, right, the limit of the partial sums is also less than 2. So we know that the summation of this series, n is equal to 1 divided by n squared. We don't know what the sum is exactly, but we know that it's less than 2, so it has to be convergent. All right, so now let's look at this series. So the summation n is equal 1 to infinity of 1 over the square root of n. So these are what the individual terms of this series looks like. All right, so the table of values of s sub n, so the n partial sums, suggests that the partial sums aren't approaching a finite number. You can see they just keep getting bigger and bigger and bigger. So we suspect that the given series is divergent, obviously. All right, how we would do this. Again, we use a picture for confirmation. So figure 2 shows the curve y is equal to 1 over the square root of x. But this time we use rectangles whose tops lie above the curve. All right, so the base of each rectangle here is the interval of length 1. The height is equal to the value of the function y is equal to 1 over the square root of x at the left endpoint, so here, here, and here of this interval. All right, so the sum of this areas of all those rectangles is the following. It's the sum of the series here. So the total area is greater than the area under the curve, right? As we see, all the area of the rectangles is greater than the total area under the curve, right, for x is greater than or equal to 1, which is that integral, all right, 1 to infinity 1 over the square root of x dx. Well, we know that this proper integral is divergent, right? In other words, the area under the curve is infinite. So the sum of the series must be infinite as well, because the sum is greater than this integral. Thus, the series is divergent. All right, so what we're seeing here, the same sort of geometric reasoning, all right, that we used for these two series can be used to prove the following test. All right, so we have this integral test. So suppose f is a continuous positive decreasing function from 1 to infinity, and let a sub n equals f sub n. Then the series, the summation from n is equal 1 to infinity a sub 1 is convergent if and only if the improper integral from 1 to infinity f of x dx is convergent. So in other words, all right, remember a sub n is equal to f sub n, all right, or we're just replacing the f sub x with the f sub n here. So if the integral from 1 to infinity of f sub x dx is convergent, then this sum is also convergent. If the integral from 1 to infinity f sub x dx is divergent, then the summation a sub n is also divergent. All right, let's do some examples. I got a bunch picked out. All right, test the series of summation 1 from n is equal 1 to infinity of 1 divided by n squared plus 1 for convergence or divergence. All right, so the function f of x is equal to 1 over x squared plus 1 is continuous, positive, and decreasing. That's important, on 1 to infinity. So we can use the integral test. So we'll integrate from 1 to infinity, 1 over x squared plus 1 dx. I'm going to replace the infinity with t, and outside put the limit as t goes to infinity of this integral right here. Well, we know that this integrates 1 over x squared plus 1 integrates to tan inverse of x, all right? And then it goes from t to 1, but we're going to look at the limit as t goes to infinity. So when I do this, obviously when I plug in 1 into tan inverse of x, that gets me pi over 4. So I just got to plug in or find the limit as t goes to infinity here. Well, if you look at the graph of tan inverse, that's going to be pi over 2. So this, when you subtract, is pi over 4. And thus, this integral 1 to infinity 1 divided by x squared plus 1 dx is a convergent integral. And so by the integral test, this series is also convergent. All right, let's talk about something else. All right, let's talk about what something is called as a p series. So the series, the summation n is equal 1 to infinity 1 divided by n raised to the p power is called a p series. So the p series is convergent if this p right here is greater than 1, and it's divergent if it's less than or equal to 1. All right, so let's look at this series. All right, 1 summation of n is equal 1 to infinity 1 divided by n cubed. All right, well, if you look here, here are the terms. This is convergent because it is a p series, right? Because it has this form, and the p value is 3, which is greater than 1, so it's convergent. It's that easy to look at and see. Let's look at this series right here. Summation n is equal 1 to infinity 1 divided by n raised to the third power, which is the third root of n. Well, here's what all the terms look like. This is divergent because it's a p series, even though the exponent is a fraction, that's okay. And p is equal to 1/3, which is less than 1. So as I go back, if p is less than or equal to 1, we can say it's divergent. All right, let's do this one. Determine whether the series of summation n is equal 1 to infinity, the natural log of n divided by n converges or diverges. All right. Well, the function f of x is equal to the natural log of x divided by x is positive and continuous when x is greater than 1. All right. This is because the logarithmic function is continuous, all right, for those values. But it's not obvious whether or not f is decreasing, so we compute its derivative. So this right here is the derivative of this, putting it in terms of x, which simplifies to the following. Well, thus the derivative is less than 0 when x is equal to 1, all right, or when x is greater than 1, that is, x is greater than e. It follows that f is decreasing when x is greater than the exponential, so we can apply this integral test. So you're going to integrate from 1 to infinity ln of x over x dx. Putting in the limit notation, this will integrate into the following here. So as you look as t goes to infinity, well, plug in 1. All right, obviously ln of 1 is 0, so this goes away. So the limit as t goes to infinity of this, well, that obviously goes to infinity. So this improper integral is divergent. Thus, this series is also divergent by this integral test.